video. Today we are continuing with another example of using the force method in order for us to determine the inflection points on the given frame. And without any further ado, let's read the task for today, where basically we have a frame which is pinned at support A and point C, and the dimensions of height are marked as H, and dimensions of beam are marked as L. In addition, we have a distributed load which is acting on member BC with intensity Q, and we need to use force method to locate inflection points in the structure. And for this task, we are going to account only for bending. The contribution from axial shear force can be neglected while solving this problem with the force method. So without any further ado, let's continue to describe on how we can solve this particular problem. So as we did on the previous video, we have to determine the degree of indeterminacy for our frame. Typically for this type of problem, we, let's say, tend to solve these types of systems which have the degree of indeterminacy as 1, as for the other degrees of indeterminacy like 2 and 3 and so on. It's not that it's not possible to solve it, but it would take too much time and too much mathematical effort in order to do it by hand. So for this frame or for this structure, we have these two pins here at point A and point C. Therefore, we're going to have four unknowns, and as we already know, we have three equilibrium equations, and there for the degree of indeterminacy for this structure is going to be 1. Next, as we did on the previous cases, we are going to release one of the constraints in our frame, and then the structure is becoming statically determinate, and of course at that part where, or at that constraint which we released, we are going to add a unit load, which in this case I decided to release the pin at point C, and then we would have a roller here and apply the 1 kilonewton load here. So we're going to have case 0, for which we have to solve the support reactions and also the bending moment functions. And then we have case number 1, for which we have to solve the same, the reactions and the bending moment functions. So without any further ado, let's continue to solve the first case, where as mentioned before, now the frame is statically determinate, and it's quite easy by using the equilibrium equations in order for us to determine the support reactions. So if we take sum of bending moments at point A, we are going to come to this conclusion that we can find the value of support reaction C0. And this 0 denotes that we are solving for case 0. Next, we do the same. We take sum of forces on y direction, and then we determine the value of A0, which is as shown here. And then if we take sum of forces on x, we are going to see that the horizontal reaction at point A is going to be 0, as there is no lateral force acting on the structure itself. Next, we continue to determine the bending moment functions, and it's a matter of preference where do you want to take the cuts from which way or which direction. So I decided to take the first cut from this side and mark this distance x, and just taking sum of moments at the cut, I'm able to obtain the bending moment functions for this interval. Next, I'll do the same, but this time I'll take the cut from right, from point C, going towards the left. And if we take some of the bending moments at the cut, we're going to arrive at this. We're going to arrive at these bending moment functions for the boundaries bigger than 0 and smaller than L. Next, we continue to solve for case 1, and now we do the same. We just apply the equilibrium equations in order for us to determine the value of the support reactions. Take sum of bending moments at point A equal to 0, and then we determine the value of C1. Next, we take sum of forces on y equal to 0, and we determine the value of A10. And if we take sum of forces on x, now we are going to have a component for A11, as there is lateral force acting on the structure, which is going to be shown as here. As previously, we need to determine the bending moment functions for case 1, and we take the same cut section as we did on the previous exercise, where this is the cut which I took, and taking some of the bending moments, we are going to arrive to these bending moment functions for this given boundary. Next, we do the same, and we arrive at this function. So to have an understanding of what we did, I made a table, a summary of results, where basically this is going to be the bending moment functions coming from case 0 and the bending moment functions coming from case 1 and the boundaries where they are applied. Next, we can apply the force method, and if we apply the compatibility, we are going to be able to find what is the value of our redundant, for which we just have to solve these two unknowns. As you may now already know, that is going to be quite easy. So now let's find these two unknowns. Let's find these two unknowns by using the integrals, and we just apply these bending moment functions which we already found into the integral, and then we are going to find the first unknown, which is going to have the following value. Next, we do the same for C11, and now we have to be careful as we have to use only the moments coming from case 1. So now we apply the integrals and we are going to get the following result. And now if we go to this equation, we are able now to find our redundant by just making the report between them. And this is going to be the value of our redundant, or actually the horizontal support reaction at point C parametrically. Now, some comment here. So as the distributed load is acting on the member BC, we expect to have only an inflection point, whereas for the other member there won't be any, as we expect a linear bending moment without any change from positive to negative. But of course, if someone wants to try it by their own self, they can do it, and they are going to get a result that there is not any inflection point. So now, as we are going to take the cut section from this side, we are going to need the value of this support reaction uh, Cy here, and we can find that by using the method of virtual work, as now we already have all the ingredients. So by just using the force method, we come to this conclusion that the support reaction Cy is going to have the following value parametrically. And what I would like to mention here is that since we take the cut from this side, our X solution is going to be starting from here going to the left. But for example, if one would take the cut section from the other side, from left going to the right, then they would take the X value from this point. This will be their base point, 0 point. But in our case, as I already decided to take the cut from this side, this is going to be my base point. And when someone is going to compare with the software, it might depend on what the software does. So for example, if we go with this cut section, maybe the software will go with this one. But then basically you just have to subtract this value which you found with the whole length. And then you're going to get the same correlation between the hand calculations and the one which you get from the software. So these things must not be confused. So now let's continue with the second option. And now we have the distributed load on top. We have the cut section here. We know everything. Uh, and in fact, here it should not be a roller, but basically should be a pin. But now, as we already found the redundant here, it won't affect the bending moment function. So we will have just these two components. So now we take sum of bending moments at the cut equal to 0, and then we obtain that this is going to be the bending moment function for our case. And if one wants to find the inflection point where bending moment basically becomes 0, and at that point is going to switch signs from plus to minus or minus to plus, we just have to solve that the bending moment m0 is going to be equal to 0. And basically we'll have this quadratic equation for which we can solve. And for simplicity, I decided to solve it in MathCAD, and this is going to be the value of x parametrically, or basically the point of inflection going from right to left. And just to make sure that what we did or what we calculated is correct, let's assume some values. So let's say that distributed load on top of the beam is 1 kilonewton per meter, and we have that h, this distance, is going to be 5 meters, distance L 5 meters. So now if we plug into this value of x which we found, which is going to be our inflection point, as you can see here, then we're going to get that the inflection point is going to be located 4.38 meters away from this base point here. And if we check with the software, as you can see here, the software is going to say that the place or the location where the bending moment switches sign is going to be located at 0.62 meters. And this 0.62 meters refers to what I said previously, where basically the base point of the software is starting from here. So from here to here is going to be 0.62 meters. But this doesn't mean that what we got here is wrong, because basically we can just subtract the 5 meters from this 4.38 meters which we found, and then we are going to go to the same result, which is going to be 0.62 meters, which comes to say that the result which we obtain parametrically are safe to be used. And if one just wants to change the values, we are going to get the correct result. So this sums up the video for the day. I really hope you enjoyed today's video. If there is any questions, please leave them down in the comment section below. Like, share, and subscribe. See you on the next video.